The Zoom session is being brought to you by the Fractal Horizon Forming. All right, for today, section 2.1, angles and their measures. Okay. They define an angle as when two half lines share a common vertex. The one side's called the initial side, another side's called the terminal side. You can think of it as a rotation of this half line into this half line, initial into terminal. If it's a counterclockwise turn, that's a positive angle. If it's a clockwise turn, that's a negative angle. And various names for various sizes of angles. Here we have an angle which is sharp, called an acute angle, because it's less than this 90-degree right angle. If it's bigger than a 90-degree angle, between 90 and 180 degrees, that's called an obtuse angle. Here, if it's just a complete 180, that's called a straight angle. These next are names that I made up. If it's beyond 180, but less from 180 to 270, I call it a breakback angle. And if it's here from 270 to 360 degrees, I date myself by calling it a Pac-Man angle. Do they still have Pac-Man? I'm just wondering. A complete turnaround, which looks like not moving the angle at all, it's 360 degrees, though that's really the same as 0 degrees. And finally, you can go more than one turn and get angles beyond. All right. Now, if you put the initial side on the positive x-axis, that angle is called putting it in the standard position. And you can measure in this the angles with this so-called circular, with a kind of circular protractor from 0 to 90 to 180 to 270 to 360. Here I mark them off by multiples of 15 degrees for reasons that'll be clear later on. The trig functions of these angles can be written down relatively simply. So now one rotation is called 360 degrees. 1 degree can be broken up into 60 minutes. That's a fraction of an angle of a degree, denoted this with a little check mark. A minute is broken up into 60 seconds, denoted by these two check marks. And yes, that's pretty much where the words minutes and seconds come from. And the Babylonians chose 360 degrees for rotation because that's fairly close to the 365 days in a year. And yes, angle measures, at least this sort, go all the way back to Babylon. So that's like as far back as we've had civilization. Math can be very, very traditionalist. All right. Now, from these we derive this degrees in minutes. We derive what's called the degrees, minutes, seconds notation, DMS. D degrees, M minutes, S seconds is well, D plus 1/6 M over 60 plus S over 3600th of a degree. So we can change DMS notation into decimal degree notation. So for example, 40 degrees, 10 minutes, 25 seconds, that's 40 plus 10/60ths plus 25 over 3600ths of a degree, which comes out to 40.173611 repeating forever degrees. 9 degrees, 9 minutes, 9 seconds. 9 plus 9/60ths plus 9 over 3600ths of a degree is 9.1525 degrees. Now, you can go backwards from decimal degrees like this to DMS. You kind of have to pull out powers of 60, multiples of 60. So for example, 40.32 degrees. Well, that's 40 degrees. Okay, that's the degrees. Plus 0.32 degrees. Now, a degree is 60 minutes. So you multiply this 0.32 times 60 and get 40 degrees plus 19.2 minutes. So that's 40 degrees, 19 minutes plus 0.2 minutes. Each minute is 60 seconds. So you multiply 0.2 minutes by 60, get 12 seconds. So you get 40 degrees, 19 minutes, 12 seconds. Or how about this? 18.255 degrees. What's that in DMS? Well, that's 18 degrees plus 0.255 degrees. So multiply 0.255 degrees by 60 to get 15.3 seconds. So it's 18 degrees, 15 seconds, plus 0.3 seconds, 18 degrees, 15 minutes, excuse me. That plus 0.3 minutes multiplied by 60, I get 18 degrees, 15 minutes, 18 seconds. There are other ways of measuring degrees. I believe there's something called gradients, where a quarter turn 90 degrees is 100 gradients. And so it's 400 gradients in a circle and so on. I believe that's used by engineers because it's decimal. So a little bit more modern than the Babylonians. But it's sort of arbitrary. I mean, 360 because of the number is close to the number of days in a year. Well, fine. On Mars, would they have a different system? But I think it would be kind of nice, mathematicians, kind of like things that are in some sense natural to the geometric figure that doesn't depend on our cultural decisions. So, to that end, they created something called radian measure. Here's the idea. If you take a circle on this circular slice out of it, it will have a radius r, and we'll call this angle theta, and call this here, this curved line here, the arc length. So it's a curved length. And the idea is that when you increase theta, s increases. When you increase r, s again increases. So we say let s be r times theta, where we measure the angle in degrees. Or in other words, theta equals s over r. You know, I should add that into the on the theta equals s over r. That's page 4. I'm going to add that into the canvas, so I'll just write that over here. So angle in degrees is the arc length divided by the radius. In particular, one full rotation, 360 degrees, is 2 pi radians, because c equals 2 pi r. That's 30 degrees equals 2 pi radians. And you divide that out. 180 degrees is pi radians. And so we get what are called unit conversion factors. Pi radians over 180 degrees equals 1. 180 degrees over pi radians equals 1 because these are the same quantity. Now you can use that to convert from one unit to another. It's a unit conversion factor. It equals 1, therefore a unit. And also it enables you to convert between radians and degrees units. For example, 45 degrees, how many radians? Well, we'll multiply by the 45 degrees by pi radians per 180 degrees. That way the degrees symbol cancels out, and 45 pi over 180, that's pi over 4 radians. Or conversely, a half of a radian, what's that? Well, a half of a radian times, now I multiply 180 degrees divided by pi radians, because that way radians cancel out. You multiply by this or by this to convert by canceling out the one in the denominator. Here, pi, the radians cancel out. 180 is 90 over pi degrees, which is about 28.65 degrees. Now, the virtue of radian measure is that it fits with the formula a little bit more naturally. For example, if we have an area of a circle, this pi slice as it were, and let A be its area, then A is 1/2 r squared theta, where it's important to measure theta in radians. If you measure in degrees, you get a wrong answer. So pi 1/2 r squared theta. For example, if the radius is 0.75 meters and theta is 15 degrees, what's s and what's a? Now remember, s was r theta, a is 1/2 r squared theta. So first we have to convert theta to radians, because 15 won't work. So 15 degrees times, you have to do radians over degrees, so the degrees will cancel out. Pi radians over 180 degrees, 15 pi over 180, cancel, you get pi over 12 radians. All right, now, so from there, s is r theta, r is 0.75, theta is pi over 12. After a bit of arithmetic, that's pi over 16 meters, or approximately 0.1963 meters. A is pi r, is 1/2 r squared theta. That's 1/2 times 0.75 meters squared times pi over 12. After a bit of work, that's 3 pi over 128 square meters, or in other words, about 0.07363 square meters. And okay, so here we'll convert radians to degrees, degrees to radians, an angle, the length of a arc length and area of a circular sector. Here we go. 7 pi over 12 radians. Well, We have radians, so we want to convert them to degrees, so we multiply by degrees per radian. So the radians will cancel. So it's 7 pi over 12 radians times 180 degrees over pi radians. These cancel, and after a bit of arithmetic is 105 degrees. Negative 40 degrees. Negative, watch out, that's a clockwise turn. Negative 40 degrees equals how many radians? Well, we have degrees here, so we want to multiply by radians per degree to convert, so we can cancel out the degrees. So it's negative 40 degrees times pi radians per 180 degrees. Cancel the degrees, some arithmetic, about negative 0.69813 radians. And here we have a circular sector where the angle is 42 degrees and the radius is 17 centimeters. What's the arc length S? What's the circular sector area A? Here we go. First, we have to convert to radians, 42 degrees times pi radians per 180 degree. After canceling the radians and some calculator work, you get approximately 0.733038 radians. All right. So S is r theta, A is half r squared theta, S is 17 centimeters times 0.733038, which is about 12.5 centimeters. You'll notice I only do one decimal figure accuracy because really I didn't do any decimal figure accuracy, 0 decimals here. So I'm going a little bit more than necessary, than really required. Certainly is not, there would be no point in doing 6 figures accuracy. The R was and the theta were not measured that accurately. A is a half r squared theta, so a half times 17 centimeters squared times 0.733038, approximately 105.9 square centimeters. So there we have that. Okay, that's this for this. Next time on Monday, what am I saying, on Tuesday, we'll define the trigonometric functions 3 ways: by talking about points on the unit circle, by talking about points in the plane, and the traditional definition using right angle triangles. And we'll get some specific trig functions of specific angles. Okay, that will do for today. Where did I put this? Okay, excuse me. There we go. All right then. We have